Okay, neural architecture, SearchNet. There's a nice blog here always. I find these. I read these blogs to understand these papers, guys. So it makes a nice summary of the paper by just referring to the paper. So if you're interested, please read this paper, guys. Okay, very nice. In this paper, authors from Google propose a search for an architecture building block using a small dataset. Because if you don't use a small dataset, as you might imagine, this step will just take so long and it will be difficult to do, just achieve some results. They particularly search for the best convolutional layer on CIFAR10 dataset. CIFAR10 is a 10 class classification dataset. So ImageNet, which AlexNet was used to train, included 1,000 categories, but CIFAR10 has 10 categories. So they do a modest experiment first. Then, when they obtain some results, they apply it to ImageNet with 1,000 categories. So just they take steps, step by step. So this NASNet model achieves state-of-the-art results with a smaller model size and lower complexity, as you can see. Well, smaller compared to some other NAS studies. It's not smaller compared to MobileNet, as you can see, but it has the best results, which makes us think that NASNet, neural architecture search, is the future of deep learning. So what is the idea? Actually, in NASNet, the general architecture is predefined and fixed. First, what they do is they have the CIFAR10 architecture. Then they transfer this architecture to ImageNet and train two new cells. About the cells we are going to talk about. They first using the CIFAR10 architecture, they train this dataset. So the architecture is fixed. It's normal cell, a reduction cell, normal cell, reduction cell, normal cell, and a reduction cell. What are these cells? These blocks or cells are not predefined. That's what the neural search will find. Instead, the authors search it by using reinforcement learning methods. So in this step, search strategy, they use a kind of reinforcement learning. I strongly, if you're just going to do neural search, guys, some of you are going to do, because I know some of you are my master students, start with reinforcement learning, because it's the best point to start. So what are these cells? Normal cells is like a convolutional cell. It will make convolution. It might have different blocks inside, but the size of the input, the spatial dimensions of the input and the output are the same for a normal cell. That's the idea. It is like, I don't know, it's like inception module. The reduction cell is a similar cell. It can contain convolutional layers as well, but the spatial dimensions of the input and the spatial dimensions of the output are different. The output, spatial dimensions of the output is smaller by 2. So it's like a max pooling layer, but a more complex one. It does not only do max pooling, but it has some convolutional layers inside. So it does a clever pooling. So it's an advanced pooling layer, advanced convolutional layer, which has many elements inside. But which elements? That's why we do the neural architecture search. So we have convolutional layer, a reduction cell, convolutional cell, reduction cell, convolutional cell, reduction cell, and in the end, we have a normal cell and softmax. That's the idea. So what they do is they apply this reinforcement learning idea. In order to find which cells are best, they start with a network. They just check the network, get some results, and by using reinforcement learning and a recurrent neural network process, which they call the controller, they train cells. This part is a bit complicated. I know you need to know optimization and you need to learn new things in order to achieve this, but you should get the idea first here now. This is a detailed RNN process. So in the end, they obtain 3 different cell types. NASNet A is this. So in the normal cell, we have this. Well, it looks like the inception cell, but it's more advanced, as you can see. There are connections here and there are connections here. The connections are not symmetric. There are different connections to different layers. And this is the reduction cell. As you can see, it has many things inside. So it's average pooling layers on identity layers and different layers. When they use this, and another one is here, NASNet B. And now let's see. These are very long experiments, guys. They have used 500 GPUs with 2000 GPU hours. Since they are Google, they can use many GPUs, guys. It took over 4 days. I mean, if you try to do that experiment with your single GPU, it would take months, whatever. And they obtained some cells. And with these cells, they've got the best place. That's how do you do it. So, if you have a network, imagine you have a shallow network, a couple of layers, but you don't just decide, you cannot decide what kind of an architecture it should have. Well, you can apply this idea, at least using a good speed up method, because it is difficult to do neural architecture search if you don't have very nice hardware and many GPUs and stuff, but still you can. Okay, guys, before we finish, let's talk about the future directions. This is our last slide. Actually, this is the last slide of the course. Since AlexNet, most existing work was focused on image classification for neural architecture search. If we do not consider neural architecture search, well, there is segmentation and other stuff, object detection. But for neural architecture search, people have been working on it for two or 3 years, and in these years they focused on image classification. So there is a lot of things to do for neural architecture search on segmentation, on object detection as well. So those parts of the field are still unexplored. If you're going to do something on neural architecture search, I strongly recommend you do something on these unexplored domains, like object detection maybe. And plus, neural architecture search can be applied to online learning problems for which the search space is continually fed. Because usually deep neural networks is applied to some domains. We have so much data, let's train on that data. But that's not the nature of data for all problems. For internet, for banking, for economics, there are a lot of data which is flowing every day. If you can construct a proper architecture, searching strategies, the proper optimization method using reinforcement learning or genetic algorithms, you can do this neural architecture on live data, which will create a live, evolving architecture. Well, and neural architecture search brought and will bring more problems. You have to combine optimization, classical machine learning, convolutional networks, recurrent networks, all problems together. That's nice, guys. It is time for these fields to collide. So there is so much thing to do. Because I'm giving a 2-semester deep learning course. I start with classical deep learning, teaching you guys convolutional networks and some recurrent neural networks. Then this embedded deep learning, we talk about architectural stuff. Actually, there are other courses that can be taught, like generative models or sequence models. But at this point, this part of the field is so unexplored that you can achieve many things if you work on this. And if you're going to work on this, good luck. Just let me know. And have a nice week. I'm going to add one video after this one, maybe next week. I'm going to explain you guys about the project presentations, how I want the project presentations to be. And I'm going to announce the project presentation date. I think that's all for week 12 and 13. See you. Bye.